This is the screencast for section 6.3, example 5, using tabular integration. This is an awesome shortcut as long as you understand how it works. We have a situation here where the antiderivative of x squared e to the x dx is our goal. We'll try and evaluate that. But you can see that we're going to have to use integration by parts. We have a product of two functions of x that are not related by a derivative. And if I made u x squared, the derivative of u would be 2x. I still wouldn't be able to integrate, but then the derivative of 2x would be 2, which makes life a lot easier. So you're probably going to have to do integration by parts more than once. As a matter of fact, I'm going to first show you how to do integration by parts on this problem so we can compare it to how tabular integration works. So I've got u as x squared, dv as e to the x, took the derivative of u and the antiderivative of e to the x, dx. And there's my first phase of antidifferentiation by parts. Now I make a new u and a new dv, again correlated to the first ones. And then I have a setup of a second integration by parts. I simplify, and I take the actual integral. So now I'm going to show you how this correlates to tabular integration. Alright, so this integration by parts is made up of a pattern, and maybe you can see that pattern. For example, this first term right here is our original u times v. U times v, and it's a positive term. So I'm going to color positive terms pink, x squared e to the x, and that was u times v here, which is also represented here by u, oops, that wasn't straight, u times v, the first antiderivative. Remember, this was dv and this was u. So u times v, and that is a positive term. Now the next term here is a negative term, so minus 2x e to the x. 2x came from the derivative of u, so that's here. And then this e to the x came from v, the next antiderivative of the first antiderivative. So that's going to be a negative term. The next term is going to be 2e to the x, again the next derivative, along with the next antiderivative. And then finally we have a plus c. So tabular integration is a great shortcut where you don't have to show integration by parts. You can simply write down all the derivatives, write down all the antiderivatives, and line them up, alternating positive, negative terms. I'll show you a short, real shortcut example now here in the now try problem. The now try problem number 21 says use tabular integration to find the antiderivative. So they're telling you specifically to use tabular integration. That's good. So I am going to make u x to the fourth and dv e to the x. So if u is x to the fourth, I'm going to take as many derivatives as I can of x to the fourth. My first derivative is 4x cubed, then 12x squared, then 24x, then 24, and then finally 0. And now I'm going to list out as many antiderivatives of e to the x as I can, e to the negative x, so be careful. E to the negative x is obviously the dv. Now the antiderivative of that is going to be e to the negative x, but then divided by -1, so negative e to the negative x. And that's going to alternate between positive and negative because of the u in the exponent is a negative x. Alright, so now I'm ready to evaluate what the antiderivative of x to the fourth e to the negative x dx is. My first term, if you remember, is going to be positive, just u, it came from u times v. So there's my u times my first antiderivative v. So my first term is negative x to the fourth e to the negative x. My next term is going to be negative, made up of the next two diagonals. So negative or minus 4x cubed e to the negative x. Then my next term will be positive, so it's still going to be a minus 12x squared e to the negative x. Then a negative, so then minus 24x e to the negative x. And finally my last term will be minus 24 e to the negative x, and then of course plus c. Now all of these actually turned out to be negative terms, but that's just how this tabular integration worked out, because we alternated a positive and then opposite and then same and then opposite and then same terms, which just so happened to correlate with the negatives in the antiderivatives.